All right, so we're going to start our conversation on radicals and simplifying radicals. I think this is going to be a new concept for you, and so a little bit strange at first, but with some practice it can be very, very easy. So the point behind simplifying radicals, right, is because there's a difference between the square root of 2 and what you did in the last unit, which was go ahead and punch that into your calculator and get 1.414. There's a difference between these two numbers. They're the same value, they mean the same thing, but this 1.414 is a rounded decimal, and so it's not nearly as accurate as the square root of 2. And sometimes we want to be as accurate as we possibly can. So it becomes necessary for us to be able to work with radicals. And just like fractions, right, we want to be able to, get a fraction in its simplest form because it makes the arithmetic easier, makes the math easier, and a little bit easier to deal with. So we need to be able to simplify radicals so that we can keep some of our measurements and some of our answers in the most accurate form possible. So the objective today is to simplify radicals involving products and quotients. Okay? Some vocabulary for you. A radicand. A radicand is anything underneath this radical sign. Anything inside the radical is called the radicand. A radical expression is any expression that contains a radical. So anything that has a radical in it is a radical expression. For example, 2 square root of 3 or square root of x plus 3. Now, how do we know when our radicals are simplified? Well, it only happens when these three things are true. When the radicand has no perfect square factors other than 1. What are perfect squares? What are perfect square factors? Well, perfect squares are numbers like 4, 9, 16, 25, 36, 49, 100, 144. Right, and I skipped a few there, but they're basically any number that you can take the square root of and get a whole number in return, right? So a radicand can have none of those factors in order to be simplified, none of them. A radicand cannot have any fractions. It cannot be fractions. We can't have fractions inside of the radical sign. And we cannot have radicals in the denominator of a fraction. It creates an irrational number, and so we're going to have to do what we call rationalizing the denominator. Okay, so for example, 3 square root of 5 is simplified because 5 does not have any perfect square factors. 9 square root of x is simplified. There's no fraction inside the radical. And the square root of 2 over 4, well, that is a fraction. There's not a radical in the denominator. Now, compare that to these three, where these are not simplified. Right? And so there is a perfect square factor for 12, and that's 4. The square root of x over 2, there's a fraction inside the radical, so not simplified. And in this guy, there's a square root in the denominator, so we can't have that. So we're going to have to work to take care of all that. Okay? Now, what's going to help us in simplifying is something called the multiplication property of square roots. The multiplication property says as long as two numbers are positive inside the radical, so this, if we can factor those radicands out. In other words, if we have the square root of AB, then we can split that up into the square root of A times the square root of B. So if we can break something down into two factors underneath the radical, we can split those factors up into their own square roots. So for example, the square root of 48. We can factor 48 down into the square root of 16 times 3. There are a lot of factor pairs for 48. We can list them, right? 1 and 48, 2 and 24, 3 and 16? Right, we just did it there. 4 and 12. So we could rewrite 48 into a lot of factor pairs, but we can choose 16 and 3. There's a reason why we'll get to in a second. And then we can split that up from the multiplication property of square roots. we can split this up into a square root for each factor on its own. Square root of 16 times the square root of 3. And the reason why we might do that is because we know the square root of 16 is 4. And so we can rewrite the square root of 16 as 4 without losing any accuracy at all. Right? 4 and the square root of 16 are both just as accurate. Okay? And so the square root of 48 can be rewritten as 4 square root of 3. And that's how we simplify. So let's try some. Right? The square root of 160. And so the idea here is to take the largest perfect square that will divide into 160 and rewrite 160 into those two factor pairs. So for this one, we know that we can rewrite 160 into 16 times 10. And we want to use 16 because the square root of 16 is 4. So we can rewrite this as the square root of 16 times the square root of 10, which turns into 4 square root of 10. Okay? And the same thing with the 72. We're going to rewrite this as 2 times the square root of 36 times 2. I'm going to shorten this a bit. We know the square root of 36 is 6. So this is going to turn into 2 times 6 times the square root of 2. 6 times 2 is 12. 12 square root of 2 is what we end up with when we simplify. One more. 5 square root of 48. So we can rewrite the square root of 48 into 16 times 3. We just saw that. The square root of 16 is 4. So I'm going to turn this into 5 times 4 times the square root of 3. 5 times 4 is 20. So we get 20 square root of 3. Okay? All right, variables. We want to also be able to deal with any variables that we may get inside of our radical. Okay? And so here's the deal. A variable with an even exponent is a perfect square. Right? Because n squared, we get n squared by taking n times n. So it's something multiplied by itself. So therefore, the square root of n squared is just n. Right? What about the square root of x to the 6th? Well, if we multiply x to the 3rd times itself, then we get x to the 6th. So since that's the case, the square root of x to the 6th is just x to the 3rd. And so hopefully you're starting to see a pattern where all we've got to do is divide the exponent by 2, x to the 10th. The square root of that is just going to be x to the 5th. And we can keep going, so on and so forth. But any even exponent is a perfect square, and when we square root that, all we do is divide the exponent by 2. Now, odd exponents are not a perfect square, but you can factor it into a perfect square, and then the same variable with an exponent of 1. In other words, n to the 3rd, we can split apart into n squared times n to the 1st. So if we want to square root n to the 3rd, then we can split this up into the square root of n squared times the square root of n, where the square root of n squared is n, and we leave the other n inside the square root. We can do that for any odd exponent, x to the 11th. If we want to take the square root, then we can split this up into the square root of x to the 10th times the square root of x to the 1st, because 10 plus 1 is 11. The square root of x to the 10th is x to the 5th. So we get x to the 5th times the square root of x. Okay? So we see we just reduce by 1 and divide by 2 to get how many x's or how many variables will come out front. Okay? And we'll try to establish a bit of a shortcut here for you. Try to make life a little bit easier. So, let's try some together, right? X to the 4th. What's the square root of x to the 4th? Well, x squared times x squared gives you x to the 4th, so the square root of x to the 4th is just x squared. Divide 4 by 2, and that's how many x's you're going to pull out. Okay? X to the 7th. Well, It's odd, so we can rewrite this as x to the 6th times x to the 1st. The square root of x to the 6th is x to the 3rd. We just divide 6 by 2. And we still have this other x inside the radical because the square root of x is just the square root of x. Okay? All right. What do you get from what is the square root of m to the 9th? Take a couple of seconds. Well, hopefully you've split this up into m to the 8th times m, right? Or the square root of m to the 8th times the square root of m. The square root of m to the 8th is m to the 4th. And so we get m to the 4th times the square root of m. Okay? All right, now we're going to start putting it all together. Numbers, multiple variables, all that kind of stuff. And if you want, you can kind of treat each piece individually. In other words, the square root of 16 times x to the 4th times y to the 5th, we can actually split up into the square root of 16 times the square root of x to the 4th times the square root of y to the 5th. Where the square root of 16 is obviously 4. The square root of x to the 4th is x squared. And the square root of y to the 5th we can rewrite as the square root of y to the 4th times the square root of y, where the square root of y to the 4th is just y squared. So we get 4x squared y squared times y times the square root of y. Okay? And that's it. Now sometimes you're going to be stuck with a couple of different radicals that you can't simplify yet, and we've got to know how to deal with that. For instance, if I split this up and take the square root of 20 times the square root of a to the 7th times the square root of b to the 8th. All right, so 20. I need to split up into a perfect square factor. So I can go 5 times 4. A to the 7th I need to split up into a perfect square. And then one other variable. And then the square root of b to the 8th is already a perfect square. It's just b to the 4th. Now the square root of 4 is 2, so 2 comes out here. 2 square root of 5. The square root of a to the 6th is a to the 3rd. And we still have this square root of a times b to the 4th. Now because multiplication order doesn't matter, we can rearrange this stuff, right? We can always multiply 2 times a to the 3rd, b to the 4th, and they'd be just fine. And then the multiplication property of square roots, we can go backwards. It says that we can always split up two factors. Well, we can always put two factors together also and just make this the square root of 5a. And then we're simplified and we're done. Okay? Think about one more. I'll try one more approach to this. Right, so we're going to factor out 18 into 9 times 2. And then we're going to factor out p to the 3rd into a perfect square, which is p squared, times the square root of p. And then we've got the square root of q to the 6th. The square root of 9 is 3, but the 2 has to stay in. The square root of p squared is p. And then the square root of q to the 6th is q to the 3rd. Now, another way to approach this is everything on the outside gets multiplied together, while everything on the inside gets multiplied together. So 3 times p times q to the 3rd is 3p q to the 3rd. And then the square root of 2p. And then we're done. Because we're taking this 2 times that p. Okay, think you got it? Well, try 10. Stop the video and see what you come up with. I'll give you a hint on the next series of problems. Try to reduce your radicand first, and then see, and then multiply. All the outside stuff gets multiplied together, and all the inside stuff gets multiplied together, and then look to simplify the radicand again. Okay, give it a shot, stop the video, and start it back up and see how you do. Did you get this? Okay. There is no perfect square factor for 6 or 15. So we just multiply the outside stuff, 3 times 5. And and then multiply the inside stuff, 6 times 15 to get 90. Then 90 there is a perfect square factor for, which is 9, so 9 times 10. But the square root of 9 is 3, so we're going to pull the 3 outside the radical. So 15 times 3 is 45, and then 10 stays inside the radical. Okay? Try 11. Stop the video, start it back up, and see how you do. All right, did you get 10 square root of 5? Again, 2 and 10 do not have perfect square factors, so just multiply everything on the outside and then everything on the inside. So you've got 5. 2 times 10 is 20. 20 can be factored into 4 times 5. The square root of 4 is 2. So you get 5 times 2 on the outside, which is 10 square root of 5. Okay? All right, here's 12. Try another one on 12. Stop the video, start it back up, see if you're right. Okay, did you get 18? So 27 had a perfect square factor, which was 9. So we can rewrite 27 as 9 times 3. The square root of 9 is 3. So now you get 2 square root of 3 times 3 square root of 3. We multiply the outside numbers. 2 times 3 is 6. Multiply the inside numbers. 3 times 3 is 9. The square root of 9 is 3. So you get 6 times 3, which is 18. Okay? Hopefully this is getting easy for you. Got another one for you to try. Again, simplify the radicand first, then multiply, and then simplify again. Okay, so hopefully you got 210 x to the third. Okay, and there's a little bit of a process here. So 7 square root of 5x, there's nothing that you can simplify out of 5x. Then you've got your times 3. 20 we can split up into 5 times 4, because 4 is a perfect square. X to the fifth we can split up into x to the fourth times x. Now the square root of 4 is 2. That's where this 2 came from. The square root of x to the fourth is x squared. So now you end up with 7 times 5x times the square root of 5x times 3 times 2 square root of 5 times x squared square root of x. Now all the outside stuff, 7, 3, 2, and x squared multiplies out to 42x squared. And all the inside stuff, 5x, 5, and x multiply out to 25x squared. The square root of 25 is 5. The square root of x squared is x. And so 42x squared times 5x is 210x to the third. Okay, piece by piece, take it step by step, and make it a little bit easier. Okay, another one here for you. Stop the video, start it back up, see if you're getting these. And hopefully you got 42t times the square root of 2t. Okay, and you can kind of see how it's broken down from there. If this is not making sense, make sure you get in during STAR or after school to get some help. This is one of those things that you're going to have to do because you're going to see it again in geometry and in Algebra 2 and on from there. Okay? All right. Now, there's also something called the division property of square roots.